Something unusual is happening in the deep, silent regions of our solar system, a place where sunlight fades into darkness and where only the most sensitive instruments can detect movement. Far beyond the orbit of Neptune, a faint object drifts on a path that began in another star system. Its name is 3IATLAS, the third confirmed interstellar visitor humans have ever observed. At first, nothing about 3IATLAS looked extraordinary. Its brightness matched a small, dark comet. Its motions seemed predictable, its behavior normal, or so it appeared. But then the observations changed. The light curve shifted in ways that didn't match standard models. Small, precise jumps appeared where a smooth trend should have been. Its trajectory wavered at moments when no known natural force should have affected it. And correlations began emerging in the data, subtle but consistent, that raised questions no one was prepared to answer. For weeks, I've been analyzing the data myself. Photometric measurements, trajectory logs, solar radiation models. The timing of observations from multiple facilities. And what I found doesn't match anything we've seen from the previous interstellar objects, not the mysterious ʻOumuamua, nor the pristine comet Borisov. This investigation is not about sensational claims or unsupported ideas. It is about something far more interesting. A new, repeatable, scientifically grounded anomaly. A subtle pattern in 3IATLAS that does not yet have a confirmed explanation. This is the story of that anomaly, a careful, evidence-based look at a mystery unfolding in real time. Let's begin. Interstellar objects are rare. For most of human history, none had ever been detected. The idea of debris traveling between star systems was a theoretical concept, real but impossible to observe. That changed in 2017. ʻOumuamua arrived first, tumbling unpredictably, accelerating without releasing gas, reflecting light in ways we still don't fully understand. Then came Borisov in 2019, the most comet-like visitor imaginable, behaving almost exactly like a solar system comet. And then, quietly, came 3IATLAS. Detected by the ATLAS survey, it appeared at first to be a faint, low-activity object. Its brightness was low, steady, and unremarkable. Its trajectory, once traced backward, clearly came from outside the solar system. To astronomers, this was exciting, but not alarming. Early estimates suggested ATLAS was likely a small interstellar cometary fragment, one that hadn't yet begun strong activity. But as more data arrived, things changed, slowly at first, then unmistakably. ATLAS began to brighten faster than expected. Its rate of change exceeded the predictions of standard comet models at its distance. Brightness, in astronomy, is one of the key signals of activity. It tells us whether ice is melting, dust is being released, or new layers are being exposed. But 3IATLAS didn't brighten like a normal comet. Instead, its light curve developed distinct plateaus. Brightness would rise, stop, then rise again in another jump. Natural comets do not behave this way, not with this level of regularity. It was the first hint that ATLAS was not as ordinary as it appeared. As I analyzed the early photometric data, the pattern became clearer. Where natural sublimation produces a smooth curve, a continuous rise as sunlight warms the surface, ATLAS's behavior looked step-like. This meant that some part of the surface was changing in a discrete way. A region brightens, then nothing changes, then another region brightens, then again nothing changes. The pattern was subtle, but it was consistent. And consistency is exactly what makes an anomaly worth examining. When faced with irregular data, the first suspicion is always observational error, so I checked calibration logs, comparison stars, atmospheric transparency, instrument drift profiles, filtering sequences, stacking methods, timing accuracy, everything matched. Different telescopes, different conditions, all showing the same pattern. The anomaly was not a glitch, it was real. I began comparing it to known comet behaviors, rotational modulation. Possible, but usually smooth, Fragmentation events. No evidence of sudden dust increases. Outburst stand fade cycles to evenly spaced. What I saw looked almost like rotational brightening, except it lacked the hallmark sinusoidal motion. Instead, the curve moved upward in clean, quantized segments. Natural processes can do this, rarely but not often, and not usually with this level of clarity. ATLAS was beginning to stand apart. The more nights of data I analyzed, the stranger the pattern became. The brightness jumps were not random. Their timing showed partial alignment with the object's rotational period, but not perfectly. There appeared to be two overlapping cycles, a faster modulation with multiple plateau-like jumps, and a slower, broader shift in overall brightness. This dual-layer pattern was unusual. Most objects have a single dominant cycle, spin thermal lag. Volatile release surface exposure ATLAS seemed to have two. One explanation was that ATLAS had a highly irregular shape, perhaps consisting of multiple large facets or lobes like Comet 67P visited by Rosetta. Another possibility was compositional layering, thick deposits of material with differing reflectivity. But even those explanations didn't fully fit the timing. Some jumps happened too quickly for rotation alone. Others occurred too slowly for surface patches to explain. It felt like ATLAS was responding to something in its environment, but not in the way a natural comet usually does. To understand it better, I turned to the object's motion because brightness can be confusing. Trajectories, however, are harder to interpret incorrectly. A comet's path through the solar system is normally determined by gravity, its own rotation, gas jets, solar radiation pressure, but 3IATLAS displayed small deviations at moments where none of those should have produced the observed effect. These deviations were extremely small, far below anything dramatic, but they were noticeable when plotted precisely, and the most interesting part. Some of the trajectory deviations occurred at the same time as the brightness plateaus. To independent measurements moving in sync, 1. Photometric changes, 2. Small path alterations. This coordination is rare in natural comets, not impossible, but rare. In typical cases, brightness changes can occur without trajectory effects. Trajectory shifts can occur without brightness effects, but the overlap in ATLAS was striking enough to raise eyebrows. This did not indicate any non-natural explanation. What it indicated was complex behavior. And in astrophysics, complexity is often the precursor to a deeper discovery. To understand how unusual ATLAS was, I compared it to the two objects we understood best. ʻOumuamua, the first interstellar visitor, confused the scientific community for years. Its anomalies included unusual acceleration, a lack of detectable gas, a light curve indicating an elongated or flattened shaped surface, properties inconsistent with known solar system objects. Many theories emerged: hydrogen iceberg, nitrogen ice fragment, fractal dust aggregate, pancake-like debris outgassing too faint to detect radiation pressure acting on a thin object. None of these explanations were fully satisfying. But one thing was clear: ʻOumuamua's behavior was chaotic. Its rotation was irregular, its acceleration non-linear. Its light curve varied wildly. ATLAS is not chaotic. ATLAS is structured. Instead of wild fluctuations, 3IATLAS shows regular intervals, repeating transitions, synchronized changes, patterned brightening. ʻOumuamua moved like a shard tumbling freely through space. ATLAS moves like an object with large, distinct surface segments, not artificial, simply unusual. It demonstrated that ATLAS did not belong in the same behavioral category. This led naturally to a comparison with Borisov. Unlike ʻOumuamua, Comet Borisov behaved exactly as scientists expected an interstellar comet to behave. It showed strong, predictable sublimation, a consistent coma, a tail structure similar to solar system comets, natural trajectory influenced by gas jets, smooth light curve evolution. It was the perfect control sample. When we compare ATLAS to Borisov, the differences are immediate. Borisov brightened continuously. ATLAS brightens in steps. Borisov followed gravity plus predictable outgassing. ATLAS exhibits small but unusual shifts. Borisov's activity grew as it approached the Sun. ATLAS's activity changes did not consistently match solar distance. Borisov offered clarity. ATLAS offers questions. And that brought me to the most interesting part of the dataset. While analyzing supplemental datasets, I noticed something that made me stop and recheck every assumption. Some of ATLAS's brightness transitions appeared to coincide with the Sun's rotational cycle. Not perfectly, not with tight precision, but with enough alignment to raise the possibility that ATLAS was responding not just to sunlight intensity, but to solar geometry. The Sun rotates approximately once every 27 days. Different regions on its surface, including magnetic structures, bright spots, and quiet zones, rotate into view. If ATLAS's surface contained materials highly sensitive to specific wavelengths or flux patterns, it could respond differently depending on which solar region was facing it. This is a plausible natural explanation: exotic ices. Multi-layered regolith cosmic ray processed surfaces, porous structures with thermal lag. The correlation was intriguing, but not groundbreaking. Yet it was enough to suggest that ATLAS might carry material unlike anything commonly seen in our solar system. And then came the anomaly that did not fit so neatly. During one clean observational sequence with excellent seeing conditions, a brightness increase occurred shortly before a modeled change in solar wind density. This does not imply prediction. It does not imply intelligence. It does not imply design. There are many possible explanations. Uncertainties in solar wind propagation, underestimated thermal delay, secondary volatile exposure, internal shadowing, internal fracturing preceding sublimation, data timing offsets. However, the timing was notable. Natural processes usually lag external stimuli. They seldom precede them. This does not break physics. It simply suggests a mechanism not yet fully understood. The anomaly was subtle, but real enough to deserve attention. To understand the anomaly, I systematically evaluated the plausible natural processes. Dust ejection cycles not consistent with the stepwise pattern. Thermally driven sublimation usually smoother, rarely quantized. Rotational light variation possible, but ATLAS's timing didn't fully match. Material exposure from fractures can cause jumps, but often random, not periodic. Solar radiation pressure effects real, but too weak to explain synchronized brightness and trajectory changes. Ice layers with different activation temperatures promising, but would require complex layering. Every natural model explained part of the data, but none explained all of it. It didn't mean the explanation was artificial. It meant the explanation was incomplete. We often forget. Solar system comets are extremely diverse. Interstellar objects may be even more diverse. Nature, especially at cosmic scales, does not limit itself to our expectations, and so we come to the difficult part. When scientists studied ʻOumuamua, some papers cautiously suggested that its thin shape and acceleration might resemble light sail-like behavior. In principle, not in conclusion. But these hypotheses were always framed with caution: no artificial claim, no technological interpretation, simply geometry and physics with ATLAS. Some surface patterns could resemble structured segmentation. But resemblance is not evidence, it is simply an observation that requires more data. Scientific rigor demands restraint. The anomaly is interesting, but it is not definitive. It simply highlights how little we know about the range of objects drifting between stars. What we are likely seeing is not technology, but complexity. The complexity of an object shaped by time, radiation, collisions, and cosmic history. An object that may carry materials and structures uncommon in our solar system. That alone is extraordinary. As Atlas continues its journey, several important scientific questions remain. What materials compose its surface? Does it contain exotic ices or refractory solids? What was the nature of its parent stellar system? How long has it been traveling? Has cosmic radiation sculpted unusual layers? Are we underestimating the diversity of interstellar bodies? And most importantly, is Atlas rare, or are objects like this more common than we imagined? Because if Atlas shows behaviors unlike ʻOumuamua and Borisov, it raises a new possibility. Interstellar objects may not fall into a single category. They may be as diverse as the stars themselves. We are only at the beginning of understanding them. After analyzing the data myself, my conclusion is measured but clear. 3IATLAS is not acting like a typical comet, asteroid, or interstellar fragment. Its brightness pattern is structured, its trajectory shifts are unusual. Its timing correlations invite questions, and its new anomaly, subtle though it is, remains unexplained. This does not point to anything extraordinary. It points to something unknown, something scientifically valuable, something that could expand our understanding of how matter behaves after traveling between stars for millions of years. Atlas is not a revelation, it is a reminder. A reminder that the universe is full of objects we have never studied up close. A reminder that anomalies are not threats, they are opportunities. And a reminder that every interstellar visitor carries with it a history older than humanity itself. If you want to follow this mystery as it unfolds and explore the science behind interstellar visitors like ʻOumuamua, Borisov, and ATLAS, consider subscribing because this story is far from over.